Welcome. In this video, I want to actually present the Thursday presentation or the sync session and release it today so that you can expose yourself to these ideas and come prepared on Thursday, possibly to ask questions, and also you'll have uh, time ahead for you to spend more time on assignment 1, and you will know what details you need to know about assignment 1, and that is part of the presentation in this one. Okay. So the agenda that I have for you is that I want to talk to you about the overall modeling strategy in the MLops, ML operations setup, and there are many components there. And irrespective of what type of modeling approach you use, whether it is a statistical learning or machine learning or deep learning, you have to use this modeling strategy in general. Okay, so by that what I mean, you'll know more detail about it later on. You need to know what measurement you are going to model, and then what is the analytical method you are going to use, or the deep learning method you are going to use. Is it a classification problem or regression problem? How do we know that you have a good model? How do we determine the good model? How do we know the error structure? Is the error structure is acceptable? The errors residuals are acceptable? All those things. And also how do you present this to with visualization and other tools? How do you present it to the subject matter expert or management and implement it in a system so that you can use it in real time or offline, or real time or offline campaigns. Okay. So that is what that's what the overall modeling strategy is about, and I'm going to go through that even for our deep learning course, right? It's important. And on the way, I will also talk to you about some more basic neural network concepts and apply modeling strategy to assignment 1, show you how to apply them, and then assignment 1 requirements, and what I expect from you in terms of submission for the assignment 1. Okay, so all those things I'm going to discuss with you. So let's just go over the end-to-end ML project. So end-to-end, the thing is, it's a teamwork. You'll be working with, you as a data scientist will be working with the programmer and also the management or subject matter expert. In order to determine what is the problem you're trying to solve, what problem is the priority for you, right? And how do you get that one? Usually, looking at the dashboard and figuring out why certain measurements are going up when it should not be going up, or why certain measurements are going down when it should not be going down. Okay, it's that's what will help you to determine the priorities of the problems to solve, and you pick up the highest priority and you start working on it, which means you ask for the right data and then do the right EDA work, which means data cleansing, preparation, transformation, feature engineering, and then creating train, test, validation splits, so that you can do the analysis and modeling. By that I mean you will experiment with the various modeling techniques. Within a regression method there are so many methods. Within a classification there are so many methods. So you'll have to experiment that, and then fine tune the model, fine tune and then tune hyperparameters. Maybe an ensemble method, you'll have to use multiple models coming together, and then do the evaluation and validation and get satisfied that your best model is achieved. I'm going to talk to you a little bit more about those things, the modeling strategy. But that's what you do, and then finally you figure out what is the best model, and then you take it to the management and as well as the SME, and present it with visuals and convince them that this is the best model, and explain the scoring mechanism, implement it in the system, and then have a mechanism to monitor that via the dashboard. So that is a full life cycle. Okay, and then it continues. So keep this in perspective, because we will revisit some of the keywords I used here later on. So going back to the basics of the neural networks, in the beginning people were thinking only perceptron is connected to the perceptron, which means the input neurons are connected to the output neuron. That's it. Okay, but anyway, that I'm going to use that to explain what is meant by activation function and some details about activation functions. But that also led to problems with the neural network, why it will not solve a problem called XOR, that is XOR, that is exclusive OR. Gates will not be estimated by the will not be estimated by the neural network. Okay, but let's just finish this part, what is meant by activation function, recalling that, and what are some different types of activation function and so on. So the input neurons, X1, X2, X1 input values from the input neurons are weighted by this W1, W2, Wn weights, and then that product, some product is added with the bias, and we apply this activation function F, and that's what this expression, mathematical expression is, and that is supposed to represent the output neuron value Y, output neuron value Y. Okay, if it is not, if it is, of course, for every observation it should be same. And we will have a collection of weights, but we will select those weights for which the average weights will give us the least error with respect to the output neuron value. That is the structure. So I already talked to you about the output neuron values, the average weights when you use it, because there are so many observations you will get it. For each of the observation you find this product sum, add the bias, and then do the activation function on it, and then see how close it is to it, right? And you keep on varying the W values, so that W values as well as B values, so that the closest, that vector W vector and the B combined together, that which gives the closest value to Y is the right one to do. But then there are so many observations you have, so for all the observations it has to come together. So there is a mechanism we have to build. And what is the mechanism? So let's think about the general process of building estimating a response surface, whether it is neural network or not, in general, and also the error function or loss function and how they are related. So the classical method is you define a function for all those points. That's a statistical learning method. Is define a surface that is very closest, that is basically going through all the points, but you shouldn't do all the points, but it should approximate to all the points, because if you do all the points, then it is great for the training, but it won't work for the testing. So we want an approximation that will also work for the testing. So y hat is an approximation to the true relationship f of true relationship between x1, x2 and y. Y hat is the approximation of true relationship between x1, x2 and y. Okay, that's what we are trying to estimate. So after the training, the weights and the weights and the x's are fixed after the training, and hence we can calculate the error. For new data, we can use the model y hat is equal to f of w1 hat x1 plus w2 hat x2. The w1 hat and w2 hats are estimated values from the data to predict y. So because then w's are known and x are already known from the data points, so for every data points in the training we can estimate y hat values, and for the test also new data also we can do the same thing. So so keep in mind, so the process is the purpose is to approximate a best surface that is closely connecting the x1 and x2 input variables to the output variable y. Of course, we use the test validation in order to see how good the prediction is happening, and if it is good, then we use that model for the production and as well as for prediction. Prediction in production, you can say that way. So there is a concept already I brought, so there is something in this example, the x1 and x2 may not weighted by this w1, the corresponding weights w1 w2 may not exactly be, after applying the function on it, may not be exactly equal to y hat. Okay, y value, that is a y hat, but it may not be exactly equal to y. Okay, and so there is an error, but then the sum of all the errors is a kind of loss that you are incurring due to selection of your specific w1 hat to w2 hat and applied along with the f function. Okay, it's a loss, and you want that loss to be minimum. Okay, so in a simple term, it is the absolute errors should be minimum. That is one loss function. So there are many loss functions one can define. For example, sum of squares of errors in regression models you have seen is another loss function. Okay, and the other one is classification model or the binary logistic model. your cross entropy is a loss function. Okay, so these are mathematically proven to be the right way to do to achieve our purpose. The purpose is to build a network that predicts our new data. So the loss function, or the error surface, loss surface or error surface, you can use loss function or error surface, loss function or loss surface, or error function or error surface. You can use that to direct your selection of W1, W2, W, those weights. That's the main point. So that should be your guide. Okay. So mathematically, conceptually think what is the right loss function, and use the loss function to guide us to search the right values of the weights W1, W2. Of course, that is the right way of doing it. Otherwise, if you do it randomly, it will take ever the time ever, and it is not the smartest way, right? So we let the loss function or the error function to guide us to search for the right W1, W2, and that principle is what is the seed to the back propagation and stochastic gradient descent for us to search for the W1, W2 values, the weights in the neural network. Okay, so keep that in perspective. Also, this is the smartest way because we don't know the function. At least we can search about the function using the errors. So you try different possible double weight values and then find out the errors that minimizes that, and then whatever that gives you W1, W2 that minimizes the total error, you are good. You can go to sleep and you have done your job. So the loss function, how steep the loss function is going to be your guide in terms of modifying continuously your weights, and that how steep your loss function is decreasing is really the first derivative. Remember that. Okay, and that first derivative is important in back propagating your error. Okay, so that's where I am going. So keep in mind why we will be looking at derivative adjustments for the weights when we do the back propagation. Okay, so that's and I have also given a separate activation function video. It's a 10 minutes video, so listen to it to understand the collection of activation functions, their derivative, because we said just now that the derivatives of the descent direction is helpful in searching for the right right weights. So now I want to go to the XOR problem, the exclusive OR problem. So before that, I want to explain some understanding about gates in electronics. Okay, so if you have let's say the four values 0, 1, 0, two input values x1 and x2, and they take values 0 and 1. Okay, then there are four possible values, right? 0, 0, 0, 1, 1, 1, and 1, 0. If an OR gate is something like this, whenever the 0, 1, 1, 1 or 1, 0 is 1 and 0, 0 is 0, then it is an OR gate. Okay, so that's easy to separate, right? It's a line that will separate that. But if you look at the XOR gate, that is exclusive OR, that means when one of them is alternate value, then it is 1. When both are same value, then it is either way. So let's say they are 0. When both of them are same value, like 1, 1 and 0, 0, they are 0. The output value is 0, and one of them is 0 or 1, then output value is one of them is 0 and the other one is 1, then the output value is 1. So that is a exclusive OR gate, and this cannot be built with the perceptron network. I haven't come to the multilayer perceptron yet. Perceptron network cannot solve this problem. So that's where eventually that was Minsky pointed out this one, and then suddenly neural network was unpopular. But then subsequently they figured out that using hidden layers, then we should be able to solve this problem. That's the idea here. Okay, using the hidden layers, we should be able to solve the problem. So what we are saying is that x1 and x2 are the input values here. -1 -1 takes -1, -1 1 takes 1, 1 and minus 1 takes 1, 1, 1 takes minus 1. Okay, this is what XOR gate is, right? And what we are saying is that, if you use the input, hidden neuron, then we can solve this problem. Okay, so I'll show you in two ways. So input values are, x1 takes minus 1, minus 1, 1, 1, x2 takes minus 1, 1, minus 1, 1, and y takes minus 1, 1, 1, minus 1 for those records. Okay, 4 records. So in this case, if you introduce the the neuron H1 and the hidden layer neuron 1 and neuron 2, when you have the categories that these categories both are 0 or both are 1, will be connected to this one, and only one of them is changed, the other one is the opposite of that, complement of that, that is represented by, captured by neuron 2. Then this will be it will output an OR gate, and then you combine with the AND gate, by these connections, then you will get a XOR output. Okay, so a combination of OR and AND will get you an XOR output. Okay, that's the idea. Alternatively, I'm going to explain it in the following way. And before that, let me go back. And how many weights are here? There are 6 weights here. 1, 2, 3, 4, 5, 6 weights are there. And then there is a bias 1, 2, 3. 3 bias also. So there are 9 parameters, 9 unknowns. Okay. Now the XOR problem can here is an example. So if you can estimate 2 linear functions, one single linear function cannot solve the problem. But if I can create 2 linear functions, then it can solve the problem, because anything above this line is minus 1, anything below this line is minus 1. So you combine those 2 lines, then you get the answer. Otherwise it is plus. Okay, so that's what this answer is. And in this example, you can see, we have specifically loaded with certain parameter values for the bias and the weights here for x1 and x2, for the hidden neuron h1 and h2, output neuron y, and we will use the sigmoid function or ReLU function. It doesn't matter either way. We can, this can be proven that we will be able to solve the problem with that gives this answers. Okay, so the values are, the weights are so much, in this case 20, 20, minus 20 and minus 20, and here the bias is 30, and here the bias is minus 10. And let's take a look at this one. So if we apply this sum product here, 20 times the input value x, right? X is let's take this 0, 0 and 1, 1. Okay, so it is 0, 0. So we are talking about minus 10. We are talking about this neuron. So minus 10 is, so it is negative. It's a negative value. So if you use the sum of negative, the sigmoid function, it's a small value, so you can map it to 0. That's correct. And on the other hand, if you have 20, 20 minus, this one, if you have 1, 1, so that is 20, 20, 20 and 20, but this time it is 1, 1. So again, and in this case, you have a very big positive value, so it's 1. Okay, so we are building. Remember that we need to build OR gates and then combine it with AND. Okay, and the 0, 1. Suppose you take, for this one 0, 1, it becomes a high positive value. So sigmoid function will give me 1. You can apply it really also. It will become the same thing. Okay, and or some modification of ReLU. Also for 1, 0, this is 1, 0. Okay, remember this is 1, 0, this is 0, 0, 0, 1, 1, 1. So finally 1, 0, if you apply that, again this is a positive number, so it's 1. So this first part maps it to 0, 1, 1, 1. Okay, now the this relationship to the second hidden neuron is applied using these weights. Minus 20 times 0, 0, this one, right? Minus 20 times this point. Minus 20 times 0, minus 20 times 0 plus 30, because the bias is 30, then it is a high positive value, so it is 1. This is the negative value, so it is, because you remember, this is minus 20, minus 20, minus 40 plus 2, so it's a negative value 0. So this is a positive value, because minus 20 plus 30 is plus 10, so 1. So this is 1, 0, 1, 1. Okay. Now if you and then this is representing the it is representing when it is positive. It is at least it's an OR gate. This is an OR gate. You agree, right? This is an OR gate. Okay. This one is also a different type of OR gate. Okay, which is when it is both are 1, then it is 0. Rest of them are all is 1. Okay, so if you combine this and this along with this gate here, you are using the values are 20 20 and the bias is minus 30, so you get 0 0. So same way, some product you get a negative number here, so it's 0. So you get a negative number here, 20 minus 30 0. You get a positive number here because 40 minus 30 is plus 10, so 1. Again here it is positive, so it's 1. Okay, yeah. Okay, so so the point is now, by combining all these three things, because of the hidden neuron network, hidden layer neurons, you will be able to solve this problem. Okay, in this case, when you combine all these three things, you will be able to solve this problem here using this kind of logic. So the other way is to look at 4 neuron hidden layer neuron, and then you can simplify this model. It's a dense neural network. Here we have 2 input neurons and then 4 hidden layer neurons. So we have each one of them getting 2 weights, right? 2 plus 2 plus 2 plus 8 here we have, and then plus bias, right? 8 plus bias, 4 bias is 12, and then we have here another 1 2 3 4, and then there is a bias here, so totally 17 parameters. If you have this one, you can solve this problem also, because each one of these will have all resolutions. These values, each of these combination of values can solve this problem using 4 hidden layer neurons. So, but in this case the parameters are different. Number of parameters are many and it's different. So the point is, now you can use hidden layers to solve a problem, complex problems, but which hidden layer to use, how many hidden layer to use, is a problem to solve, because nothing is known to us in a real world problem. So this is a very highly constructed problem for XOR, exclusive OR problem. But when you have hundreds of millions of data points, and and maybe hundreds and thousands of input variables, then you have a lot more variations in the parameters that you have to test, identify, estimate, verify, all those things. It's a very complex situation, but you will have lots and lots of parameters to resolve. That's my main point. So we talked about the STAR problem, but let's go to the strategy, modeling strategy problem, right? The point is, we are searching for the values W1, W2, W3, W1000, right? And when you increase the number of features, then you will have more number of parameters to estimate. When you have more number of parameters, then you will have more variance in the prediction. When you have less number of parameters, that's the situation here. When you have least number of parameters, a simple model is a linear model. If you have least number of parameters, then you are not really capturing all the variations in the data. So your model becomes biased. And on the other hand, when you are estimating with too many parameters, then your model has high variance in prediction. So the sweet spot is really reduce the bias and reduce the variance. Okay, reduce the bias and reduce the variance. So that is something like this in between. So here it is reducing the bias because it's now more closer to the data, and it is also reducing the variance because I am not introducing too many parameters, but I introduce probably here, the way it is looking at, probably it's 3 or 4 parameters, polynomial function actually, right? For our visual, I'm saying. Okay, so the good fit is, the good spot is here, and that is what this picture says. It is a matter of managing your prediction error using training and testing. This is the training based prediction error, and the low model complexity means lower number of parameters, high model complexity means higher number of parameters. So the more the number of parameters you use, you will be able to reduce the error, prediction error for the training. Absolutely. In fact, you can have absolutely zero error, prediction error, if each of the points, as in here, if each of the points is considered as a parameter, then you will have zero error. But that's not a good model because it won't fit the testing data. Because you have perfected it for the training, it won't fit that for the testing data. Your testing data will have high error here. So it has passed the best possible situation. You are somewhere going here. When you go to the zero closer to here, the error will be here somewhere, right? So much higher here. So the way to solve your problem is that you make sure that you use the training and testing to guide you to stop at a time when the test, in this case validation, remember that, validation error, it's not a test error, validation error, because you are searching for the best model. Once you determine the best model, then only you will use it for the testing, okay, remember that. So this is for the validation error, this is the training error. So when the validation error starts increasing, stop, don't further increase your number of parameters, because you will be introducing high variance. So that's one strategy, okay. The other one is can we get additional tools to help us out? There is something called regularization, which introduces in the loss function the number of parameters, or the sum of values of the parameters, or sum of squares of the values of the parameters. These are all three different adjustment, regularization for the loss function we make, so that the loss function in one shot takes care of this, the method of identifying the sweet spot. Okay, so in that case, you will use a cross validation. Remember that it's not a model training and versus validation, but it's a cross validation. Okay, so that is a strategy you'll have to follow. But on the way, see the problem with the. Let me go back to this one. Okay, very important point I want to address first before I go to the momentum on the. Momentum along with the gradient. See, if you take a simple, quadratic problem, minimization, then mathematics will give you first derivative, second derivative will give you the minimum point. But can we get the same answer using a numerical method? Okay, because oftentimes we may not know exactly this beautiful type functions, but it may be some other type, very complex function, but nonetheless we want to get an idea, understanding how this numerical method can help, and that our methods are always going to be numerical, okay, because we don't know this function. Okay, so here is the method, what is called the Newton's method. The Newton's method says you take at any point, you start with any point, and then you take a derivative. That means this is the derivative. Where it cuts, evaluate the value of the function, and then you take derivative again at that point, and see the difference, So the value, the difference here is that from here to here, I'm talking about only from here to here. Okay, it's very close to 16 minus 4, something like like 12, right? 12 units here. So we reduce the 12, we reduce the we are going towards this, the 0 point here, this flux point here, but what is helping us is the reduction, the derivative is what is helping us to move in the direction of the 0. Okay, so in the next point, it is here 2. At 2, the y value is 4, and we want to take the derivative again at that point. Okay. And that gives me derivative function, the tangent function, and then it cuts here into something around 1. Okay, and again I do the value. So the reduction in the x square. We know that we are going towards 0 because this function value is decreasing. It came from 16 to basically around 4, and then it came down to 1, and then it comes down to 0.5 square, and so on. Okay, so the gradient is the guide. That's what I want to tell you. The gradient function is the guide, and that's what we are going to use, stochastic gradient or first derivative for adjusting the the weights. You remember that? The weighted, the back propagation will use the gradient. That's the main point, okay? So, in this slide, I have actually calculated and I'm showing you how this is approaching, value by value, but I already told you this is what they, in the previous slide, I explained that to you. So that is one part of it. And Newton's method, Newton-Raphson method helps us to do that, beautifully. Mathematical, numerical methods, people do it. But in neural network, it's a different problem because we don't have a function, okay? So how do we get this solution, right? We don't have the function. We only data points. So we are kind of, emulating those ideas. So derivative is your tangent, right? The weight and the gradient is what is needed for you. And then there is some learning rate is also needs to be adjusted. That is the change in the weights, okay? Remember that. That is, so the gradient is giving us to us, and the learning rate is giving. Learning rate times the gradient is our, change in the weight values. That's the direction of the change in the weight values. And the second, another adjustment subsequently the scientists made, the neural network experts made it. That is called the momentum factors. So where we are talking about at what speed the, the changes have to be accommodated. Okay, so the momentum factor is gamma, the learning rate is eta, and this will help us to move out of certain local optimums. Together, these two together will help us to move out of the local optimum, as well as at the same time move towards the lowest error. Okay, so generally gamma is between 0 and 1. It's a kind of search parameter. So we usually prefer that gamma to be around 0.9. Eta is small when gamma is large, and eta is usually very, very small. Okay, momentum helps to jump out of the local optimum, and it is a version of Newton-Raphson method. So it's not anything new, but they kind of made it workable for neural network, which is just a collection of data points. We don't know the function. Okay, totally, we don't know the function. So that's the I wanted to get your attention to those details. Now I also want to define what is meant by stochastic gradient descent. See, the gradient descent sweeps through the entire training data to update the weights, okay? Or it could do in batches. So you remember in my first example, I was taking one observation and showing it to you how the calculation was done. But then you have to do this for, if I have 10,000 samples, then I have to do it for 10,000 samples, okay? And what stochastic gradient descent helps us is as follows. It performs a parameter update for each training example, okay? But it can take just a random sample. It doesn't have to be, it takes a random sample of samples, sample data that we have for model building. It takes a random sample, subset of the random sample, and then does the gradient descent calculation for each training example, okay? But it is only a sample of observations, not for every observation. Batch gradient descent performs redundant computation for large data sets as it recomputes gradient for similar examples. So we don't want to do that way, and SGD, stochastic gradient descent, does it for sample data within a batch, okay? And it is usually, therefore, it's faster. So putting all these things together in terms of the optimization, the goal is to get the optimum loss as quickly, that is minimum loss as quickly as possible. Gradient descent is the crux. Modifications are made to make sure convergence is happening, and it is happening quickly. Momentum is a way to get convergence. A similar method is to use RMS prop, root mean square propagation, where we change the dynamically eta values. To accelerate the process, both momentum and RMS is used. It's called ADAM when it and it is ADAM in short, meaning adaptive momentum estimation. ADAM is very widely used, addresses both A and B, that is the convergence and how quickly it needs to be, it will be approaching the lowest loss. Hyperparameters are alpha, the learning rate, beta, momentum, and beta 2, RMS, epsilon. The epsilon error. Okay, RMS epsilon here refers to how much reduction is acceptable in the loss. Okay, so that we can, it's a kind of stopping rule. So the generally the default values are beta 1 is equal to 0.9, beta 2 is 0.999, epsilon is, let's say, 0.0001. Okay, something like that, or in this case 0.0